So this equation they give you in this problem, it says if you drop something, why isn't this the one that dropping something? Yeah. If you drop something after this long, it will have gone this distance. The neat thing about 16, so anywhere you go on the face of the earth, this changes a little bit. Basically, everywhere you go, it's the same acceleration that anything experiences toward the earth. You guys semi with me? This number 16 is actually the correct number to have there based on what that pull of gravity is. That's why it's 16. It's not just 16 because they made the shit up. And that's it would be 16 here. It's 9. Well, it'd be 4.9 for every other country in the face of the earth because we're the only ones that don't use metric. So 16 because we use feet, and it'd be 4.9 for everybody else because they use meters. You have to know that to do this problem. No. So this is how far it's dropped, and this is how much time. So if you right before you drop it, 0 time has gone on, so this drops 0. The minute I drop this thing, 1 second later, it's not quite a full second, is it? So if I dropped it from 16 feet up, 1 second later, we'll have dropped 16 feet. Maybe. So it says, the Grand Canyon Skywalk is 4,000 feet above the Colorado River. And it costs a lot of money to pay for it way in advance. I don't know if anybody's ever tried to do it. You know about the Skywalk? They built this thing. It's a glass, not glass, but it's see-through. So you can walk out on and go, look, oh my God. Most of us will just watch other people do it because too much money and good Lord, it's like months in advance. Anyway. How long will it take a stone to fall from the Skywalk to the river? So it's 4,000 feet from the Skywalk to the river. Right now, I'm having trouble not thinking about Star Wars, but yeah, you make S 4,000, solve for T, so you can see how much time it's going to take to drop that far. Maybe? No? Yes? No? Yes? So if I would have said how far will it have dropped after 2 seconds, you would put a 2 in for T to see how far. Well, I want it to drop 4,000 feet. How long will it take to do that? Well, that's 4,000. And I can solve for T to see how long it's going to take it to do that. Yes? No? Yes? Are you guys all right? Okay. Anything else from homework stuff? Is that all right? All right. Still an optimistic fool. Take that as a good sign. We are going to get into chapter 12, since there's no questions. Chapter 12 is still in the book. It's 13 and 14 that aren't. We're probably going to do minimal amounts from there anyway, so it's going to work out okay. So, here's what we're getting into. The first part of chapter 12, I got you ready for a long time ago. Because I didn't see any reason not to. So, let's just review. Two functions, right? Let's just do some really, really basic review. Can somebody tell me what g of -1 is? Yeah, how do you do that? What do you do? Plug -1 into this function, of course. Become a plus. Does that sound familiar? Remember this? So function notation is just substitutions. Can somebody tell me what point? I know a point that the g function goes through. What point does g go through? From what we just did. Be careful. Point has two parts, at least. -1, -2. It's going to go through the point. When x is -1, the output is -2. So this function goes through that point. That's another reason why function notation is so useful, because I can see the full point in my work. Okay, I like it. It's always nice for there to be a point and you can see it's even better. So what about, let's ante this up a bit. What about f of g of 2? I like it. I asked you this kind of question before. And that actually is what chapter 12 starts off with, is this. But you see why I did it when I did. It's a natural next step. So what am I putting into f? Whatever the hell g of 2 is. So what do we always do when we have something to simplify? Don't we start at the innermost and work out? That's what order operations kind of tends to do. So it's f of whatever the shit g of 2 is. How do I do g of 2? Yeah, put a 2 in, so it'll be 3 times 2 plus 1. So it's f of 7. And then I just put a 7 in for f. Yeah. 49 minus 4. 45. I like it. I like it. I like it. I like it. So the basic idea of function notation is to substitute something in. This kind of question is, I don't know what I'm substituting in yet. Well, let me figure that out first, so then I can substitute it in. All right. Let me push this even further. What is this? F of g of f of 1. Alright, so I can just go crazy with this, but where do I start? What is the first thing I do? Because that's the innermost. I'm plugging something into g. I got to figure out what that something is first, and then I can figure out what this whole thing is, so I can know, oh gosh, so f of g of, what's f of 1? -3. I guess every step is just substitution. That's the basic idea behind function notation. I substitute the value in for the variable. So now, what is g of -3? Yeah, it'll be -9 plus 1, -8. And then what's f of -8? -64 minus 4? 60. Minus 4. Right? Yes. Alright, let me stop for a minute. This is all kind of old news here. Now here's something I don't think I ever pushed you before. I mean, we've done basically all this before. I've never made you do this. Take a minute and try to figure that out.
It's just going to be a long equation.
So what am I asking you to put into G? F of x. What is f of x?
X squared minus 4.
What do we do every time for all these? I replace this with what it was, and then I put it in. Right? So I'll replace this with what it is. What is f of x? X squared minus 4. And then I take that and I put it in. So g of x, just remind you on the corner, I'm going to put g of x was 3x plus 1. So what's g of all this mess? It'll be
3
times all this mess. Function notation is so single-minded. It's like you have a whole bunch of shit in there, you just take that whole bunch of shit and you put it in. And then I simplify. Right? Good. So open I'm just going to say 13. All right. How are you doing so far? This is kind of nice. Hopefully, this is kind of like, oh yeah, we did this stuff before. It's all right. Function notation, just substitute stuff in. Yeah.
I just have one question. When you're putting the g of x into it, there's a 3x.
No. I'm putting f of x into g. So I'm putting this in here.
Oh, okay.
So what's it say? G of this. So I'm going to put this into g.
No, I understand.
I like it. So f of g would be the opposite, right? What would f of g of x be? Careful how you say it. This is not times. This is f of, right? It's sort of the same idea. How would you say this? How do you say that? Say it. Just say it. Square root of 9. Not square root times 9, right? It's the same exact idea. The square root is a function. What am I taking the function of right now? 9. Square root of 9. I love that shit. So if I don't know what the function is, I still say it the same way. This could be the square root function. I don't know. Actually, I know it isn't, but in general it could be. So this is f of 3x plus 1. So I pick 3x plus 1 up and I put it into f. F is thing squared minus 4. That's its rule. What am I squaring? 3x plus 1. And then I can FOIL this out, blah, 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 to simplify it. You guys? So I'm taking what's inside. What do I always do with the function? I take what's in here and I put it in place of x in the function. Doesn't no matter what the hell's inside there. Very single-minded. Okay. So here's what's new. And this is a really nifty idea. Make sure. Oh, let me say this before I get too far. I don't know if this came up before, but the textbook way to write that is really, really crazy. But this is what it looks like. This is the textbook way to write this. Oh my God. And I agree. There's no reason for this, really. Yes, it's just like, and this captures how students feel sometimes in this class. This is like f of g of x. But why do that? Why not just write it like this? And then it makes more sense. Then I can see this is sitting inside of this dude. That makes more sense. But if you see this, so if I saw this, what's a better way to write that? Yeah, h of f of x. So if you see this notation, you can immediately replace it with the regular notation. There's some notation I disagree with it existing. I've already brought up square roots. But they exist, so we got to know what the hell they are. Okay, I like it. Can't read you guys. I think we're all just tired. Okay, so here comes the new stuff. So one thing I want to remind you about being a function, what does it take? This is going to be a huge ask, but does anybody remember what the definition of a function was? Yeah, for every x, there's only one y. It's my, this chair is crazy. That's going to be a neat part. All right. That's all right, Kendall. I set you up, man. Okay, yes, whoever said that. For every x, there can be only one y. For every input, there can be only one. And, I remember it because it's related to this show called Highlander, but if you're unfortunate enough to never have seen that, then for every input, there could be only one output. That's what it takes to be a function. And it kind of makes sense. If I throw something in the air and I say, where is it 3 seconds later? So my input would be 3 for the function that describes where it is. I can't get 2 different values. I'm like, what the? Where were you on the night of February 11th at 10 p.m.? I was at the 7-Eleven and I was over at the Hyatt. Who the hell are you? What are you talking about? Where were you? One place, right? Or teach me. Or 2 different places frequently. Are you guys? So you remember that whole discussion we had, the function. The idea, the definite function is related to it needing to describe something that physically makes sense. Now, I'm going to impose an extra condition, so it's a special kind of function. So let me ask you this. I am thinking of a number right now, and when I square it, I get 16. What number was I thinking of? 4. You're wrong. Ah! I was thinking of -4. So, sorry. But the point I'm trying to make is, it's still a function because 4 only has one output and -4 has only one output. But I want to define a function where I could be a detective and actually work my way back to know exactly where an output came from. So I basically want this to work both ways. For every x, there's only one y. For every y, there's only one x. Let me get you guys to agree with me. Because, for example, if I say I took the square root of something and I got 2. Now I'm not trying to set you up for failure. What is x? 4. That's it. Because if it was -4, it would have been what as an output? Square root of -4 is 2i. So square root seems to be okay. I can work my way back with square roots. Because what does the square root look like? Is anybody able to do that in the air? What's the square root look like? Don't make the symbol of the square. I mean, graphically. Yeah, it looks like this, right? So at every x, there's only one place where it is. That's why it's a... But for every y, there's only one x value that leads me to that output. But what does a x squared look like? Because that's how I tripped you guys up earlier. I said I squared a number and got 16, and you guessed the wrong one because what does it look like, of course? What? What does an x squared look like? You're thinking about a cube root. Maybe.
Oh.
That's a sideways parabola. That's a little beyond us. There we go. So x squared looks like this, right?
Yeah.
So there are outputs that have multiple places they could have come from. So if I'm at 16, I could have come from 4 or -4.
So x squared will have like a mirror image, basically.
Yeah, I can't let that happen.
Yeah.
So to be a function, it can't come back on itself like this, because then it won't pass the vertical line test, right? To be what I'm going to call a one-to-one function. So this is going to be a special kind of function, a one-to-one function. Not only can it not come back on itself like this, but it can't come back on itself like this either. So it's got to pass what kind? This doesn't pass a certain kind of test, but this one does. Horizontal line test. I love it. Because if a horizontal line goes through my picture more than once, that means that output had 2 different inputs that came to it. Then I can't be a detective. I can't work backwards and tell exactly who it was. It was you 4. No, it wasn't. It was you -4. No, shit. I don't know. Put them both in jail. Right? Or have the dragon kill them both. Okay. So I have a vertical line test to see if something is a function. I have a horizontal line test to see if something is a one-to-one function. Now, why do us crazy-ass math people do this? Because if it is a one-to-one function, I should be able to get a way to go back. If I know the result, I should be able to work my way back to tell exactly where it started. So I should be able to find the opposite of the function. So, example. So if I cube a real number and get negative 8. Can we work our way back to what it must have been? Where did that come? What did I cube to get negative 8? And what did you just do to figure that out? So if I cube a number and I get negative 8. Cool? The answer definitely, because when I cube negative 2, I get negative 8. But what did I actually do to negative 8 to work backwards? What did I do to negative 8 to figure out what that was? Cube rooted it. Because what's the opposite of cubing? So what we're talking about is, if it is a one-to-one function, I should be able to find an opposite function that undoes what that function did. Funky. Maybe. All right. So let's. So for example, if I double a number and get 48, what was the number? Obviously, if I double a number and I get 48, what number did I? 24. What did you do to 48 to figure it out? The opposite of this. To work my way back. The only time that's going to work is if I have a one-to-one function. Otherwise, it leads me to 2 or maybe more answers, and then I can't tell for sure.
Are those examples of one-to-one functions, or are they just analogies?
No, those are examples.
Those are okay.
Yeah, these are one-to-one functions. Right? And I don't know if you guys remember, parabola looks like this, but a cube looks like this. Does it pass the horizontal line test?
Yes.
Yes, no horizontal line goes through more than once. I like it. Doubling a number is this function. Right? Y equals 2x. Is that cool? That's what the double a number function looks like, 2x. And what does it look like? A line. Right? Does it pass the horizontal? Well, yeah. It doesn't turn back on itself. Maybe. All right. We're going to attack the same idea from multiple directions. So I need to lay out there the idea of one-to-one function and kind of the idea of where we're about to go. If it is one-to-one, I have to be able to figure out the opposite function, something that undoes what it does. And why does that make sense? Because these are, I didn't even write these as functions, but you figured it out by doing what? The opposite of this. So, that's more of a definition approach. Now I'm going to take a graphical approach, and then I'm going to take an algebraic approach. Just going to overload all of your senses. So let me make a very straightforward function that is one-to-one. All right, so let's see. Oh, let's see. So I'm going to have here, there, here, and then let's do one more level up here. Those numbers, sort of. So this is my function here. Is that one-to-one?
Yes.
Because it passes the horizontal line test. So vertical line test is just to be a normal, run-of-the-mill function. And then I got this extra level of special kind of function. And you have to pass another test. That kind of makes sense. Anything you want to try to get more certification for, you have to pass another freaking test. So there's a function, it's like, I want to become a one-to-one. You got to pass it. Oh, I did. Now it's one-to-one. All right. Now, what point is this? My crappy ass numbers, but what point is that? -3, -2, right? Right? What point is this?
0,
0, -1. And then this is 1, 3, and this is 3, 4. Okay, now stay with me. say this a lot, I'm sorry, but this is so awesome. It's kind of beautiful what happens. Let's see if you guys agree with me. This function, did I tell you what the function is? No, I just gave you the graph, which is almost better. I've done the work already. I'm going to call this function f of x. Whatever this function is, when I put a -3 into it, what do I get out? -2. When I put in 0 into it, I get a -1, and so forth. Is everybody with me on that? Okay, I like it. This is related to those problems we saw earlier this semester where they just gave me a picture and they asked me what f of 1 was. And we're like, how the shit do I figure that out? They didn't tell me what f of x is. I just had to go where 1 is and, oh, f of 1 would be 3. Because that's where they put the point. Now, if my whole intent with this, I know it's 1 to 1, so now I want to graph the inverse function. So what should the inverse function do? It should take -2 and they could go back to -3, right? This function makes 0 go to -1. What's the opposite function going to do? Make -1 go back to 0. Does that make sense? Are the addition and the subtraction functions, are they opposite functions? Yes, right? So if you add 7 to 1, you get 8. How do you get back to 1? You subtract 7. So the opposite function should take the outputs of this dude and get me back here. How do I say that really quickly? Flip the freaking points around. Right? What is my inverse function? What's my opposite function going to go through? What points? And the symbol for inverse kind of sucks a bit. Ooh, you're a good pen. This is the symbol for the inverse function. This doesn't mean 1 over f. They just picked this and they're really, really dumb. I don't know what happened the day they picked this, but too bad. That means opposite function. So if my function was x plus 7, the opposite function would remarkably be x minus 7. So, because when I put a 2 in here, I get a 9. And when I put a 9 in here, I get back to 2. So if this one goes through 2, 9. Is everybody cool with that? That one goes through 2, 9. Is everybody cool with that? This one has to go through 9, 2, because it's supposed to take the output of 1 and bring it back to what it was. It undoes what the other one did. That's what I would hope something called the opposite function would do. Okay, I can't read any of you. Some of you guys that can read. All right. Some of you guys are like, when does this stop? It's not the end yet. Shit. It's not that far into the class. Stop looking at the clock. All right. So now watch. I'm going to, in green, I'm going to graph the, I can graph the opposite function even though I don't know what the shit it is because I know what it does. So what points does this guy go through? -2, -3. It'll do to -2 to bring it back to -3. It'll undo what the function did. And it also goes through -1, 0. Yeah, it goes through 3, 1. 4, 3. Better add myself a little 4 on there. All right, so if I graph this now, it's going to go through -2, -3. Where am I at? -1, 0. 3, 1. And then 4, 3. Now, can anybody tell me, do you see any symmetry here? Now, I got a crappy drawing. You can base on it's not that bad, right? But it's kind of. Can anybody tell, even based on my horrific scaling of this, where the mirror is? There's a mirror here somewhere. And what's really funky about the mirror for this is I can go on either side of the mirror. So I'm like Alice. I can go into the mirror and then my reflection's on the other side. Holy shit, that's trippy. Not sure what I'm on.
If you right through the center of it, it's like...
Yeah, right in the center of this stuff. So it's actually the line, I should have dotted that sucker, but I won't. It's the line y equals x. It flips around the line y equals x. Think about why they make sense. What did I do to the points to make the points for the opposite? I flipped them. So what's it going to do visually? It's going to flip over the y equals x line. I should have made this, if I would have went through this line, its reflection would have been itself. right? So what if the function went through 2, 2? The inverse would go through 2, 2, because it's right on the mirror. It's not going to go anywhere. It's not going to get reflected. Maybe. Okay. So I really remember this green function should undo whatever the blue one did. So what did the blue one do to -3? It made it become -2. So the green function should take -2 and bring it back to -3. It should undo whatever the other function did. What that leads to, I don't know if anybody agrees, but that's a neat shape. I'm sorry, it just is. So whenever you do inverse functions, they do end up looking like Nazca lines or something. You know what those are? Yeah.
Is that considered the line of symmetry?
Y equals x is the line of symmetry for inverse functions. I like
Does
that.
that one pass through 0, 0?
Oh, y equals x does, yeah, definitely, because 0 equals 0, so it goes through 0, 0.
Okay.
Yeah. It goes through every point where y is x. So it goes through 0, 0, 1, 1, 2, 2, -1, -1, -2. Yeah.
Will every one-to-one function have a line that does that?
If it's one-to-one, that means an inverse must exist,
Okay.
which means there will be another function that is symmetric reflection through the y equals x line. I like it. This is appropriate responses. That is kind of trippy and nifty, I'm hoping.
What happens if we have imaginary numbers and why do that's like more complicated?
Yes.
Okay.
Everything we've done this whole semester, we could go back and redo with imaginary numbers. That's a lot. Because even just graphing a simple graph, I'd have to have a whole other thing. And if you type into Google graphs of imaginary functions or something, they have to use colors to represent the level of imaginative to it. Because to do an XY plot, the X has another axis, the Y has another axis, that's 4 dimensions, dude. So let's not go there. What they do with, stay with me now, watch. What they do visually is the 4th dimension is color. That's why if you look up imaginary or complex graphs, they'll be unbelievably colorful. Because color is the 4th dimension. That by itself is trippy. Yeah. So normally the blacker it is, like the darker it is, that's the more complex it is. And then the lighter it is, that's the less complex. So it's more real. I like it. So it is nifty. Yeah. And you get to all these things like Mandelbrot sets and all this kind of, it's neat. Yes?
I just have one question. So if it's G, like the line of symmetry is G equals X, it will never be vertical at that point? Or will it be vertical? Like the line of symmetry? Or like the actual function itself, will it ever be vertical?
If I'm talking about inverse functions, that is the only line of symmetry. That's it.
All right.
I like it.
Inverse function.
Parabolas have an axis of symmetry, and since they move, they take their mirrors with them. The idea of inverse function is the x and y flip. So I don't care what the function is. If it is one-to-one, it will always be flipped around this line because that's the definition, is that you switch the x and y. It's supposed to undo what the other one did. Okay, I like it. Okay. So, I like to give you this kind of problem where I give you a picture, and then you have to, on top of it, graph the inverse. And that should be relatively simple. You just identify points, switch the points, and then regraph the points. And you know it should end up being symmetric, so you kind of know what it should look like. So what does this mean algebraically? What if I give you a function and I say, find the inverse function? Don't graph it, find it. Shit. This is what I love about this. You do exactly the same thing. What do I mean? Because I'm not going to have a graph. I'm not going to do anything graphical. This is purely algebraic. So they give me a function like and they say find f inverse. So it's a cube, so it passes the horizontal line test, right? So now watch, this is too awesome. You ready? What I do graphically to find the inverse? Well, what is it I did?
You choose 7.
Switch the x and y. I like it. Where's the y in this? Let's bring the y back. I'm bringing y back. Yeah, f of x is y.
All
right, now watch. No. Other teachers might not do this, but I have to do this, and I'll see if you guys do this. I'm about to apply an idea. I'm not about to do something algebraic. What I'm going to do is I'm going to rewrite this statement, but I'm going to switch x and y. So that's so beautiful. What do you do graphically? Switch x and y. What do you do algebraically? Switch x and y. Because that's the basic idea of an inverse function. One guy's output should be the other guy's input. So if I switch, so what I always do though, since I'm not doing something algebraic, what I do is I draw a little dotted line. I've done it ever since I learned this. Because I'm not doing something, and then I just rewrite it, but I put an x there and I put a y there. And I don't stop there, because I'm not done yet. I've got to resolve for y. Think about why this makes sense. How do I start to solve what I just wrote down, solve it for y? What do I do first? Cube root, I love it. Why is the y stuck? Because of the cube. All right, kill it. So aren't I already starting to do all the opposite shit? What am I trying to get? I'm trying to get the function that is the opposite of this one. So this process, even if I didn't do this idea makes sense. If I switch x and y and solve for y, I'm going to undo all the stuff that's there. I'm going to do all the opposite things. So what I have so far, I've got very Christmassy. Oh, these are the two ones that are working. So I got one last thing to do. Add 2. So I get y equals the cube root of x plus 2. So I can put officially f inverse. Sure. What's this guy do first to an input? If I put a number in fact, let's do it. What is f of 4? Yeah, so it'd be 4 minus 2 cubed. So 2 cubed is 8. I like it. Is that cool? So what should f inverse of 8 be? It should take 8 and make it become 4 again.
Yeah.
Should undo what the first guy did. Well, let's see if it does. So f inverse of 8 would be the cube root of 8 plus 2. 2 plus 2. 4, yeah. Right? Is that right? No?
Yes.
So when I discover the inverse function, I can take a second to make sure it makes sense. It's supposed to, whatever this guy has come out for a number, this should take that and bring it back. It should undo. This guy did something to 4, and he's going to undo it. It's the lame superhero team, the inversers. Snap everybody back.
Give you a golf clap for that one.
Huh?
Give you a golf clap for that one.
Oh, thank you. That's all right. I don't deserve much more than that. All right, so let's try another function out real quick. And then I got a little handout, of course, for you guys to try. So let's do, oh my God. That's the ones that are working. Yeah, let's do a really gross one. I like it. Unless you know that. So you guys might pick up on the fact that I'm using odd things, odd powers, odd roots. Those are the ones that are going to have nice, clean inverses. Because a parabola doesn't have an inverse. Now you could say square root is, now watch. I want you to realize why that's true. Here's a parabola. You could say, but the opposite of that is a square root. But you see how that's not the whole reflection. It's missing this piece, isn't it? It's not a true reflection, so that's not, they're not technically inverses of each other. Okay. Just a little tiny point, but still. Okay. So what do I do first here? Yeah, bring that y back. Then I switch the x and y. And then I just start going to town on that. Go ahead and take a minute and try to solve that. for y. The very first thing you need to do is start solving this. Yes, subtract the 8. Isolate the radical. Now I can kill the radical.
You have to raise both sides.
Yeah, raise it to the 5th power. Please regard, if I ask you to find the inverse of a function and you end up with this, don't multiply that out 5 times. Leave it like this, okay? Yes. Just like I did here. Look, I had x minus 2 cubed. I didn't have x cubed, blah, 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 blah. So now I've got x minus 8 to the 5th equals, those cancel. And I just have a couple more things to do. Next thing is, add 5. So now I got x minus 8 to the 5th plus 5, and the last thing, of course, is divide by 2. So I get f inverse is x minus 8 to the 5th plus 5 divided by 2. Now watch, this is kind of cool. Why does this make sense? What's the first thing that would happen if I put a number in here? And this is what I forgot to do earlier when I did this, but let's try a number out. So if I put a 1 in there. Yeah, the first thing I could do to that number is multiply by 2, right? What's the last thing I'm going to do to something over here? What's the last thing I would do here? What's the last thing I would do?
Add by 5?
No. Divide by 2, right? I have to do the top, and then I can divide by 2 at the end. First thing here is multiply by 2. The last thing there is divide by 2. That sounds freaking opposite so far. And you can keep going. This one then subtracts 5. This one adds 5. This one adds a 5. That was a 5 power. This one adds 8. That one subtracts 8. I mean, yes, maybe. I like it. So here, what do you get from this? Oh, it gave us a gross one. I should have made it 2. My bad. I want to get something I can actually get a nice number out of. So f of 2 is the 5th root of 4 minus 5, the 5th root of negative 1 plus 8. What is the 5th root of negative 1? Let's just take 5 off to multiply by negative 1. Negative 1. Some root of some kind of 1 has to be some kind of 1 if it's anything. So I get f of 2 is 7. So what will I get if I do f inverse of 7? I'm going to have to get 2, or this whole thing goes to shit, right? So if I put a 7 in, 7 minus 8 to the 5th power plus 5 over 2. 7 minus 8 is negative 1 to the 5th is negative 1 plus 5 is 4 divided by 2 is 2. Good Lord. I got back to 2. I know I did that kind of fast, but still, that's the idea. You actually check yourself. Okay, so let me see if you guys can figure out this kind of question, and then I'll give you this handout. What do you think about this? Let me marry this idea with the earlier idea. Barely any writing required for this. Let me see. Can you guys figure out what's going to happen here? F and F inverse are what's of each other? Opposites. So they cancel and get x. It's like, what is the fifth root of 21 to the fifth power?
21.
What is it?
21.
21. Oh, yeah, no roots. Because whatever this guy does, he's going to undo it. They kill each other. And so now you see, that's just a shortcut way to say this one undoes whatever this one did. But what's a better way? They kill each other. Right? I don't want to do the fifth root of 21. Well, that's going to be 10.7. I don't know. And then to raise it to the fifth power. No. And why would I do shit? Because they're going to undo each other anyway. So you can just think of it as they kill each other, as we've been doing this whole semester. So everything we've killed have been inverse functions. That's why they killed each other. I like it. I like it a lot. So that's why when you have x plus 8 divided by 8, you don't do this, because division and addition are not inverses. How could they possibly kill each other? Alright, so let me shut up for finally. Let me give you guys this. This whole side here, don't worry about the side with excessive amounts of writing yet. Only worry about this side. Do these problems.